Really sorry about that. Um, Good afternoon, everyone. I welcome you all to the Exun Talk session for this year. Founded in 1992, Exun Plan is the computer science and technology club of Delhi Public School, RK Puram. We hope that you enjoy today's session. Our speaker for today is Mr. Monojit Choudhury. Dr. Choudhury is a principal researcher at Microsoft Research and is general chair of linguistic of the Panini Linguistics Olympiad and the founding chair of the Asian uh, Linguistics Olympiad. Today, he will be delivering a talk titled "Why Language Understanding is the Hardest Piece of the AI Puzzle." So, without further ado, here's Monojit sir. Right.
Uh, Thank you, Ashwin, and thanks to Exun for inviting me to give this talk. This is very, exciting as well as nostalgic for me because I think I had spoken in 2015, Exxon. Yeah, I was just checking my emails to find the date. It was 2015. So 7 years later, again. Of course, that was a different talk, and I'm sure it was all different people because for it's 7 years ago. So people who are here at in class 12 now would have been in class 5. So I doubt if they were in the talk at that time. um, and yeah, and a lot of things have changed in the field of computer science, especially in the field of artificial intelligence, in these 7 years. Now I work in the field of natural language processing. Natural language processing, as many of you know, is about how we can make computers understand and generate or speak like humans do in natural languages, as opposed to programming languages. Uh, and there are many problems that I work on in this field, and I work also on Indian languages, some of the problems specific to India. I won't have time to get into the details of my work, but I will mention some of the things that I have been working on. But in this talk, what I want to do is give you an overview of why natural language understanding is the hardest piece of the AI puzzle. First of all, I want to convince you that this is very hard, and then I want to give you some of the ideas that today the artificial intelligence community is trying to use to solve the problems, and where we are. So that's the gist of the talk. And please feel free to ask questions in the put your questions in the comments, and I might take them up in the middle of the talk, or most likely at the end of the talk. We'll have some time to discuss. Right, so let's start with the very foundations of artificial intelligence. So in 1950, Alan Turing, who is also famed for being one of the first people to have propounded AI in the way that we understand it today, said something like this: that it is not difficult to devise a paper machine which will play a not very bad game of chess. Are there imaginable digital computers which would do well in the imitation game? Now, imitation game, as many of you might know, and there has been a movie called Imitation Games, which is a biopic on Alan Turing. Very nice movie. So, imitation game means to imitate humans. Computers have to imitate humans. So, it can be in many, respects. So, one imitation game that Turing talked about was, while humans can, sorry, machines, by paper machine he means just computers. So while machines can beat humans in chess, can machines play chess like humans do? The two questions are very different, actually, and we will see in a moment why they are different. But before we delve into that, let me tell you the more common way people understand Turing test. So it's like there is a person in the middle sitting, who is the human judge, and there are two you know people or machine or whatever the person doesn't know behind a veil, and they are interacting. There's a conversation going on, and this person in yellow in the middle has to tell, just based on the chatting or the text conversation, that whether it's a human or a machine on the other side. Now, if this machine here sitting in the left side kind of manages to fool the human judge to believe that it is actually a human certain number of times, those are details, but if it the idea is, if it manages to fool the human to believe that it's not a machine but another human, then the machine passes the Turing test. So in effect, the machine has to imitate the behavior of a human, and then it passes the Turing test. Now, there are quite a few things which are interesting here to note, right? I mean, there are so many challenging problems in the world. Like, I would say playing chess is much more difficult than speaking language, maybe because I can speak, most people can speak, a 3-year-old can speak. By 5 years, humans can speak very well, but no, not all people can play good chess, right? I know the rules, but I'm not a great chess player, and most 5 years don't know how to play a chess. So somehow chess seems harder than language or imitation game in some sense. But Turing was very prescient. In 1950, he sort of guessed that that imitation game is going to be much harder for computers to solve than chess. And most of you know that chess is solved. I mean, human grandmasters are easily now beaten by computers, and we achieved this in early 2000s. However, in 2017, you see, this is a quote from Bill Gates. The biggest breakthrough in AI will be when computers can read and understand information like humans do. So, what it means is the problem that Turing stated in 1950 is still not solved in 2017. Right? If it were solved, Bill Gates would not have made such a statement that biggest breakthrough in AI will be when machines understand language. In fact, we have made a lot of progress in this field of language understanding. But even in 2017, machines could not solve this very simple problem. Suppose I tell you this. There are two statements. The man could not lift the child. He was too heavy. Question is, what whom does he refer to in this sentence, in this pair of sentences, right? So is it the man or the child? The man could not lift the child. He was too heavy. Who was too heavy? And everybody, I have tested it on my son when he was 6 year old. And you can test on, I mean, of course you guys will understand, you all will know, but even younger children can answer this question. Okay, it's the child who is heavy. Now take the second sentence. The man could not lift the child. He was too weak. Who was too weak? Now it's the man, right? And humans do it seamlessly. Almost everybody gets it immediately. Now, computers find it extremely difficult to answer this question. Until 20, if I'm not wrong, 2019, this problem was not solved. 2018, 2019. There's a famous challenge. This is called Winograd Schema Challenge in the world of natural language processing. And there are many puzzles like this. And the computers have to, I mean, the task is to solve this puzzle. And till 2019, machines did subpar performance on this task. Only very recently, in last 2-3 years, we have made some progress here. So indeed, it's a very hard problem which humans can solve very easily. And that kind of gives this notion that language understanding is as hard as artificial general intelligence. So artificial general intelligence means a machine which is generally intelligent. So if you look at most of the machines today which are so called AI or intelligent machines, they solve one task or just a couple of tasks. One task meaning it might be a great chess player, it might be a great driver like self-driving cars, or it might be a very good spelling corrector, it might be a very good translator, it might be a very good image summarizer. So you give it an image and it will say what is happening in the image. But these are all single tasks. There is no machine which can do all of these things and behave. I mean, typically what you think of an intelligent person is able to do, it's able to do all of them, right? So that's what is the notion of artificial general intelligence. And many people think if we can solve language understanding, we can solve artificial general intelligence. because language understanding is one of the hardest problem, or technically it's called the AI complete problem. AI complete meaning if you complete this problem, you complete whole of AI. I mean, loosely speaking. People who know complexity theory a little bit, you would have heard of NP complete problems. So AI complete is similar to NP complete. So it's one of the hardest problems in AI. And if you solve it, you solve essentially all problems in AI. So what we are going to discuss in rest of this talk is what makes language understanding such a difficult problem. What are the properties of this problem, and what are we doing today, and are we any closer to solving this problem? Now, to start with, let me give you some facts to contextualize the problem. So there are hard problems, and there are not so hard problems. So this is a 2018, I think, chart from some journal, and what it shows is on the left hand side there are a bunch of capabilities which a machine must solve in able to be qualified to be called as intelligent, and these are further broken down. So tasks are at high level: cognitive capabilities, natural language understanding, social and emotional capabilities, and so on. And they are further broken down into, let's say, recognizing known patterns and categories, and so on. The rating is defined as follows. So green means computers can do nearly as good as humans. This is on in 2018. So in 2018 computers were able to do as good as humans, then it is green. Yellow means computers do as good as 50% of the human performance. I mean, 50% of the humans. So median performance, sort of. So that's yellow. And red means it is less than 25 percentile, or the last quartile. So red means we have a long way to go. Now, if you see which are the red ones, so the first two are generating novel patterns, categories, logical reasoning, problem solving. These are red. Creativity is red. Then the other bunch of red is social and emotional sensing, reasoning, social and emotional output. So everything to do with social and emotional capabilities is red, and then natural language understanding is red. Now it's very uh, obvious that creativity is going to be red. Creativity is one of the hardest thing. Even it's hard for humans, right? Not all of us are creative, or even judging if somebody is creative or not is hard. I mean, let's say scientists are creative, artists are creative, and building a scientist or building an artist, is difficult. Building meaning, writing a program which will do science or which will do art. So naturally these are hard problems. Similarly, social and emotional sensing is hard, because again, humans also find it difficult often, and I will give examples. But also, if you think of it, emotion is something which is very hard to even formalize or define mathematically. And if you can't formalize or define something mathematically, it will be difficult to solve using computers. But natural language understanding, why that would be hard, right? Language is more logical. There's a grammar, there are rules you can apply, and so on. Now, if you look at the right hand side of the graph, right, it's even more interesting. It says when these problems are going to be solved, when are they going to get green? And the axis shows 2010 to 2080. And if you see for natural language processing, it's sometime around the deep blue point, right? So I mean, the not the deep blue, the cyan sort of point there. So that's around 2060, 2060, 2065. So it will take so many years, according to this survey, to solve this problem. Now, the only harder problems are, as I said, are creativity, which is going to take 10 more years, and social and emotional reasoning, which is also going to take approximately 10 more years. So it's one of the hardest logical problems to solve. And I'm always, whenever I show this, I make a joke that, hey, look, this is a great field to work on, because at least there will be enough problems till I retire. In fact, there will be enough problems till you guys retire, because it's going to be another long 40, 50 years till we solve it. So it's a good area to work on. Yeah, but jokes apart, what's common to creativity, social and emotional, processing, and natural language understanding? This is where the cue might lie, that why it is hard. And I want to give you the answer first, and then I will give you the examples. So, Ludwig Wittgenstein, many of you would have heard his name. He is one of the most influential philosophers of the last century. And he did his work between the two world wars. So, 1918 to 1940s is the time when he did most of his influential work. And he has written volumes on language. And one of the thing, I mean, what is of interest to us about why language is hard is, I'm just paraphrasing what he said in one of his famous essays. He said, language and games both use rules. So there is a set of rules for chess. There is similarly a set of rules for language. However, there are more than one language game at play. What he means by saying this, by this is, when you are playing a game of chess, the rules are fixed for everybody. The rules are universal, and everybody has to follow that rule. There is a definition of winning, who wins, and that definition is same for everybody. However, that's not the case for language game. The definition or the rules of the game evolves along the way as you play the game. So, therefore, although we speak the same language, we cannot always use that as the basis of coming up to the same conclusion. And this is the reason why often there are misunderstanding. Often you can write, in puns. People can be sarcastic, ironic. People can understand the same thing differently, so on and so forth. Now, how? I mean, let me give you a very simple example to illustrate how the rules of a language can evolve. So, very simple thing which all of you will be aware of in Indian languages, we have three levels of addressing to a person: aap, tu, and tum. So, aap is very formal. Tum, I mean, I'm using the Hindi words. In all Indian languages, there are equivalents. Tum is the familiar, but in between somewhere, and tu is informal. Uh, so there are rules of whom to call what, right? Now, you usually would call your friends as tu, but it's unlikely that you will call your parents as tu. Although in some culture, I have seen mothers in old films, Dharmender's films and Amitabh Bachchan, I have seen they call their mother by tu, but father will be aap. So these are social rules. You will call your professor aap or your teachers aap. But can these rules change? These are basic rules. Can this change? It often changes, right? So what happens is, I meet sometime, for the first time, I meet somebody in a formal place, let's say in a conference. I will call that person up. Even if that person is younger to me by a few years, I might call that person up. We become very good friends. Next time we meet in some other casual place, maybe a park or somewhere, or a cafe, and we are discussing something, we start calling each other tum. Now, that also requires some sort of a negotiation. I can't just jump and start calling tum. Sometimes I take permission. Okay, can I call you tum? Sometimes it's like, okay, I mistakenly call this person tum once, and the person does not, react, and in fact tum, calls me back with tum, and then that's an established norm. Now we call each other tum, and then we go to a bar, and one day we start fighting on something, and we start calling each other tu. So, you know there are no set rules for language. Now, this was a easy to understand examples. I'll give you a few more examples which will make it clear that it's not only social norms like this, but also meanings of words can change, right? And those rules also change. But before that, I want to tell you a very interesting experiment that people had done in 2018. This was done by Facebook, and many of you might have 2017, yeah. And many of you some of you might have heard about it. What they did is as follows. So once, how are these chess programs built? If you think about it, right? How do you teach a computer how to play good chess? So one way to do it is, you collect a lot of data of grandmasters playing chess, and then feed it to a machine learning algorithm. The algorithm looks at, for what kind of patterns, what kind of moves the grandmasters usually choose, and what kind of moves eventually led to a win, which ones led to a loss, and so on. And based on the machines will learn. Now, Google around that time, 2017, thought of a new idea. They thought, okay, what if I make two computers who are trained with the rules of the chess, but not with really grandmaster data, and they start playing with each other? And they can keep playing forever, right? They can play millions of games, billions of games, and they can learn from their own mistakes. So it's the same program playing against itself, and it's learning over time. Now, as it is learning over time, it is getting smarter and smarter and smarter. Eventually, when such a model plays against humans, they just beat human much more easily than the models that were learned using human game playing data. Why? Because the strategies this models implement are very different. They would have come up with very different strategies which grandmasters have no clue. So when the game progresses, the grandmasters get completely confused that what the hell is happening, and actually in the process they get I mean, it's easy to even beat a human. So these programs, Google named them as AlphaZero. So zero because it uses zero data. It plays against itself and learns. So there is a series of models. AlphaGo Zero is for uh, for the game of Go, and so on and so forth. So it was very successful. So Facebook thought, okay, let's make two chatbots, let them talk to each other, and let them learn from each other. Over the time, they will become better communicators. Eventually, what happened after the experiment ran for maybe a week, the chatbot, let's call them Bob and Alice, the same program, by the way, let's say two instantiation of the same program, one is called Bob and one is Alice, is chatting like this. I can, I, everything else, dot, 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 balls have zero to me, to me, to me, and so on. Absolute nonsense. However, it seems like Bob and Alice are understanding each other. Something is happening, some communication is happening. So they have invented their new rules of language, new rules of negotiation. And therefore a lot of interesting things came up in the media. For instance, Facebook shuts down controversial chatbot experiment after AI has developed their own language to talk to each other. Robots have now developed a new language and they are going to take over humans. All silly stuff. I mean, media is always silly. That's not the point. But the point is this experiment actually shows what I call the curse of Wittgenstein. you know the what happens for chess or the game of Go, or for that matter any game, does not apply for language, because language doesn't have fixed rules. So naturally the rules of the game itself evolves as Bob and Alice are chatting, and therefore they have invented a new language which no humans will understand. This was bound to happen, and this is actually not a controversial chatbot experiment. It is a badly designed experiment. They didn't foresee this happening. Okay, few more examples. So this is a personal story. I was in the US and in visiting the Grand Canyon. And Grand Canyon is really grand, as the name suggests, right? Fantastic. So while coming back, I was boarding a bus, and the driver asked me, "How did you like it?" I said, "Yeah, it's very nice." The face of the driver, uh, you know, really went sad. And she looked at me and said, "Only very nice." First, I did not understand what she meant. Then she said, "Wasn't it really awesome?" Then I got it that I'm in the US and very nice actually means not good. And in the US, good starts from awesome. So this is a meme which actually shows this stereotype. I mean, this is a sort of a stereotyping, so don't take it literally, but it has some truth in it. So this shows the distribution of what people would expect when somebody says pretty good, good. So pretty good would be average, good would be, I mean, see the top curve. So good would be something a little better than average, awesome will be far better than average, and so on. But for Americans, anything from average to upward is awesome, and anything nice and all those things are something which is poorer than average and not very bad, and so on. Now, why this is interesting? this is interesting because we are talking of the same language, English, but it is used so differently in different geographies. And these are norms which geographically and independently have evolved. And a machine which has to imitate a human has to somehow either know this norm or learn it through conversation. I learned it because while talking to the person on the fly. I didn't read a grammar book to learn that. So the machine has to learn it on the fly. There are no set rules. So that is the point again, and it varies by geography. And in fact, you don't have to get to such complex examples. A very simple statement: I saw a monkey with a banana. Now, what's the image that comes to your mind? What's the meaning? And most of you will think of this, right? There's a monkey sitting with a banana in its hand. Can you think of any other meanings? Think. I'll give you a few seconds. Yep. So it could be this, right? I saw a monkey using a banana as I would see a monkey using a telescope. Or I saw the monkey, but the banana was with me. So English allows such construction. I saw a monkey with a banana, so I was with the banana. Or even worse, saw is a verb which also means to cut somebody with a saw. So I sawed a monkey with a banana. So the monkey had the banana, I had the saw, and I sawed the monkey. Or I sawed the monkey using a banana saw. So you see, just a simple sentence and so many different interpretations. There are more actually. And the interesting question is why, when I showed you the first time this sentence, I'm sure most of you would not have thought of all the interpretations. Some, one or two maybe, but not all. And why we always go to this image and never even think of these images, right? So this is something fundamental to human language. So the language by itself is ambiguous, and there are ways due to which it becomes very specific. I mean, the meaning is determined. And what are these things? So when you are processing language, it's not only important to know language, which is what I say by linguistic, by that I mean linguistic knowledge, but you also need world knowledge. You need to know that banana is not an instrument of seeing as telescope is. So that's world knowledge. You need common sense reasoning. So yes, I could saw a monkey, that is cut it into pieces using a saw, um, but common sense reasoning would typically say that is probably not the interpretation or the common interpretation. Then there are contextual knowledge which might change your interpretation. So for instance, if I had told you that this monkey has been pestering me a lot, I got very angry, eventually I took a saw and I saw a monkey with a banana, then the total sense changes, right? So that is contextual knowledge. I gave you a context, and in that context something else made sense. And of course, I already talked of the socio-cultural norms, the example of awesome being used in different ways in different cultures, and so on, right? So all these things are part of language, and they are, I mean, these are not peripheral part of language. These are core central part of language. And if you want to build any language understanding system, all of them have to be solved. And that's why, language understanding is AI complete. It's equivalent of solving AGI. Actually, common sense reasoning, as often people call it, is one of the hardest problems in itself. So for instance, the example of Vinograd schema, the man uh, could not lift the child, he was too heavy. This common sense reasoning, right? You have a I mean, you have a frame of thinking that, what does lifting mean in this sense, what would mean if something is heavy, and all that. So you use all this knowledge, and this is what typically uh, cognitive scientists call common sense reasoning. And this is extremely important and very hard to model. Okay, so let me come to the second part of the talk. How does then natural language processing work? Right? What can we do today? At a high level, there are three kinds of systems. that we can build: rule based systems, machine learning systems, and hybrid systems. Hybrid is a combination of rule and machine learning. I'm not going to talk about hybrid, but I will tell you a little bit about rule based and machine learning systems. Many of you might already know this, so it will be a repetition, but maybe in the context of language, I can give you some interesting examples. So rule based systems are where, engineers sit with linguists and write rules, and these rules are, just things like, oh, if the sentence starts with a verb and the verb is this, then the chatbot should respond in that way. If the sentence starts with this and ends in that, and the in between there is a word which is blah, then the chatbot should respond in another way. So just using these kind of rules back in 1964, 66, Weizenbaum, he was a professor at MIT at that time, built a chatbot called Eliza. Eliza was supposed to be a counselor sort of a chatbot. You know, uh, is something troubling you? I'm bored. Do you know anyone else who is bored? Maybe. You aren't sure. I don't really know. Why don't you really know? Well, I haven't really asked. Uh, so the conversation looks pretty dumb by today's standard. Today's bots are much smarter. But just with rule based system, you know, Weizenbaum was able to do this. And Weizenbaum thought, as any, serious scientist will think, this is a horrible system. And he was almost going to throw it. But then when it got out and some people started using it, lot of people thought, wow, this machine really understands. Absolutely no understanding is going on, right? It's just some simple set of rules and pattern matching, and based on which they're responding. So this got people thinking. And today, even today, this thing of thinking machines as smart and really understanding things is called the Eliza effect, even when they don't. And it's an inherently human property. We humans tend to, ascribe meaning. I mean, the machine might have not meant anything. It might just be a bug in the program, but we tend to say, okay, this might have happened because of this reason. Because humans always try to find reason and rationality behind what happens, right? I mean, why India lost this match? We'll find 20,000 reason, but don't think that it was just a chance, right? So that's what Eliza effect means in specifically in the case of technology. But the point is that with rules you can build such systems. The problem is they don't scale. You have to write maybe thousands, maybe hundreds of thousands of rules, and imagine a engineer or a group of engineers sitting and writing these rules, right? And scaling these systems up and scaling this for many languages is extremely hard. So the first revolution that happened in NLP from this rule-based system was this data-driven AI, and this happened around 1990s. So the whole idea is you take a lot of language data, train. There are algorithms sitting here in the middle which learn from this data, and then you build a system. The system is used by user. User generates more data, and eventually, the machines get smarter. So there is a positive feedback loop. This is how most machine learning systems work today. So imagine you are using a translator or a search engine. You are giving a search query. It's trying to answer. You might not like it. You reformulate the search, or you go to the second page and try to click on this, and the search engine is taking cue from all of these sections, right? You are not clicking the first 10 and going to the next page and clicking the 20, let's say 15th link. So the search engine knows that the first 10, 15 links or 14 links are useless, and only the 15th link is useful. So this way, as more and more people start using AI systems, they eventually become smarter. But are they really understanding language? That's a different question. We will try to address it in a moment. But this is how most AI systems work today. So essentially, more data you have, these systems will be better. And another good thing about this is, see, it is agnostic to the language. You want to build a system for Hindi, Chinese, or English, or Arabic, doesn't really matter. The training or the learning piece remains almost the same, only data changes. So they are very scalable systems. Now, what kind of data do you need? I don't know how well you can see the slide, but here is a problem from Linguistics Olympiad, which I think Ashwin was mentioning when he was introducing me. So I do spend a lot of time, designing this kind of puzzles and running these competitions. It's like Math Olympiad or Physics Olympiad or Informatics Olympiad, but it's in terms of the kind of problems you get, it's closer to Informatics Olympiad. But these are like logic puzzles. So in this problem, you are given two languages. One is Yongom and the other is, of course, English. So there are 11 sentences in Yongom and their translations in English. And you are given some new sentences in Yongom and asked to translate it in English. Now, will you be able to do it? It turns out that this is a very solvable, it's hard problem, but it is very solvable problem. And you can look at the patterns and try to decipher the grammar of the Yongom language, and eventually you will be able to translate the new sentences to English. So this data, where you are given the Yongom sentence and its English translation in in natural language processing, it's called a parallel corpus. Parallel because the two sentences are parallel to each other. They are same meaning. So you have 11 sentences here, and you sort of cracked part of the Yongom grammar. You know how many sentences a machine typically needs to solve the same problem. Typically it will need 1 million sentences. And to make a really large scale good machine translation system, like you see in let's say Google translation engine or Bing translation engines today, they will require um, close to several million, like tens or hundreds of millions of sentences, and the more the better. So they require a lot of data, and that's a typical problem, because getting this kind of data is expensive, and getting it for all kinds of languages that you are interested in is even more difficult. Now, what happened in 2015 onwards? I mean, the technology is old, but in 2015 onward, we started seeing the effect of what is called deep learning in natural language processing. Now, deep learning, I mean, if you know about it, great. If you don't know, just I will tell two things. One is, in classical machine learning, uh, that is the machine learning before deep learning, you have to uh, specify the features that contain the information. By features I mean, okay, to solve this problem, or to translate this sentence, you have to look at what is the next word, what is the previous word. So next word, previous word, what you should look at, these are called features, and an engineer should define the features. Features are typically independent of language. Features are also usually universal, in the sense that features for one task typically also is useful in another task. However, you have to still define the features, and sometimes these systems are as good as their features are. In deep learning, you don't need to define any features. Just pump in data and it works. It works like magic. And actually, with deep learning, we have been able to made a leap, you know, in how accurately we can solve some of these hardest problems. But the catch is these deep learning models are huge. And I just want to give you some sense of how huge they are. So in one way to measure the size of a model is in terms of how many parameters it has. So if you think of a line, a linear equation, right? Ax plus by is equal to c. That's an standard equation for a line. So this equation has three parameters, a, b, and c. So suppose I give you some data points and tell you, predict, what happens when. So maybe let me say I give you a data point that if I buy this much amount of potato from a place, the cost is this. If I buy this much potato from another place, the cost is this. And I give you some data points, and then I want ask you to interpolate. Now, typically, the cost of potatoes will be similar across cities, so it will only depend on quantity. So it will be like ax plus b sort of a equation that you get, right? So you will fit a curve, and you will say, okay, I can predict. Give me just 5, 6 data points, and I will learn a, b, and c, and I will be able to predict. Now, when you are making the same thing with for translation, so translation is effectively the same thing. A translator, a search engine, they are effectively the same thing, just that instead of two parameters a and b, and or three, a and b and c, now you have, let's say, millions of parameters or billions of parameters, and you are trying to fit a very complex curve, which looks like nothing. I mean, it's multidimensional, not even a line in 2 dimension. It's let's say 1,000 dimension, and it's very complex curve, right? And you can't even visualize it. Nobody can visualize. So how many such parameters are there in a model gives how big or strong the model is. Now you see in this left diagram shows how these models have grown over the past 2 years. I think the BERT is a model which came in 2018 and GPT-3 came in 2020. So just in 2 years, you see these models have grown in so much size. And this model, GPT-3, which is one of the most famed NLP models, it has 180 billion parameters. So A, B, C, like that, 180 billion of these variables, which it has to learn from the data. So naturally, it requires a humongous amount of data that it requires. By the way, this is not the biggest model today. So this came in 2020 May, I think. And but in 2021 September, there was another model, Megatron Turing NLG, which came from Microsoft, and it has 530 billion parameters. And I know that people are now working on 1 trillion model parameters. So it's like, this is a logarithm scale and it looks like a straight line. So it's like increasing in leaps and bounds. And these bigger models are doing better, but are they? So they can do some amazing things, like AI can now translate as well as humans. Or, if you give GPT-3 to respond to a philosophical article, it will write amazing things. You can read it for yourself. I don't have time, so I'm not reading it out. So they can do amazing things. But they fail on very simple things. So here is one example, one study that we did. So the problem here is that of natural language inferencing. What does it mean? So suppose I say, let's look at the first example. Suppose I say name one or name two is adjective. So let's say um, Narendra Modi or Sonia Gandhi is the prime minister. Prime minister is not an adjective. You put some adjective. Let's say Narendra Modi or Sonia Gandhi is Indian. Okay. Now, this is called the premise. And the hypothesis is, let's say Narendra Modi is Indian. Now, the question is whether this hypothesis is entailed by the premise. If you were given the premise, can you also say that the hypothesis is true? And the answer is, in this case, no, because it's a or. When I say Narendra Modi or Sonia Gandhi is Indian, it could mean both of them are Indian, or it could mean only one of them are Indian. And I really don't know who. The premise doesn't say it. So when I say Narendra Modi is Indian, I have to say, neutral. I really don't know. It doesn't entail. If I say, Narendra Modi uh, is or yeah, how to okay, let's keep I mean, take another example. If I had said Narendra Modi and Sonia Gandhi are Indian, then of course Narendra Modi is Indian will be entailed. So the task is given a premise and a hypothesis. You have to say whether the hypothesis is entailed by the premise or not. And even this simple task that I just, the example that I just gave, all these models fail. These are on the right hand side, you see the accuracy of these models, these big models that I showed in the previous chart, right? They all fail. Their accuracy is 1%, which means, I mean, they totally fail. Yeah. So there are many such simple examples, and these models totally fail. So what is happening? On one hand, they can solve so many hard problems, they can translate as good as humans, and then they fail in such simple, things. So for instance, the second one, name one and name two are from country one and country two respectively. And then you ask, name one is from country one. Is it entailed? Yes, of course it is entailed, but this all methods get it only 55% time right, not always right. So they fail in very simple cases. There are many other things where these models fail. Here is another example. So here are a bunch of tweets, and you can stare at them for a moment and think what's common to these tweets. So what's common here is all of them are mix of multiple languages. So let's say the first tweet, Kibrisa Gel Digim and all, is mix of Turkish and German. Similarly, the lowermost tweet is a mix of Arabic and French. So in India, we mix Hindi and English all the time. So linguists call this phenomenon code mixing or code switching. And actually, all these models, even the big models, fail utterly when they have to process this code mixing inputs. And this is one of a problem I have been working for last 10 years in our group. So we call it Project Melange, where we are trying to build technology that understands and processes code mixing. And also we ask, an interesting question, that why, when, and how do people code mix? So I'll be happy to talk more at the end if there are questions on this. But yeah, the code mixing is one place where these models fail badly. So not only simple examples, but very simple things, but just two languages makes they can't process, even when they are trained with both languages, of course. So this kind of gave some scientists this kind of led some scientists to think about whether these models are really understanding anything. And like Turing test, they came up with something called an Octopus test. This was in 2020, so just 1.5 years ago. So the test is very simple. Imagine two friends A and B are stuck in two islands. They have nobody to talk to, but there is an underwater cable and they are talking to each other through that cable, communicating with each other in English or any language you will. And there is a super smart octopus. It's much smarter than all our models or any human or anything, right? All our models, let's say, not humans. And this octopus actually now comes and cuts the cable and sits in between. It transmits what A sends to B and B sends to A. So the communication is not disrupted. It sees all that they are talking, and it sees for maybe a month, a year, and starts learning the language. At some point, it thinks it knows enough language, and then it thinks, okay, let me play a little mischief. So whatever A says, it does not relate to B. It tries to answer it by itself because it thinks it knows, right? Learns the language. The two questions are whether A will be ever able to figure out that it's not talking to B anymore, but it's talking to an octopus. And if you think through it, you can read the paper if you want to. Actually, they argue that A might never know, actually. So the octopus might look like it actually, to A, it might look like it is actually, he or she is actually talking to B. However, you know, there are other repercussions of it. Suppose some strange animal is found on the island and A is attacked by that animal. And A is describing that animal to B to, get some idea of how to, uh, what's the strategy for escaping from this animal. And will the octopus be able to answer that? No, never. Because in the exchange between A and B, they never talked of this new animal. So there's a chance that A will just die, but B actually knew the solution. So uh, this is called the Octopus test. And through the Octopus test, what they try to bring out is these large models might look very, intelligent and might use language as humans do, but they are not understanding anything because they don't have what is called grounding. They don't have a notion of the reality, how the real world looks like, and therefore we shouldn't say that they are really understanding language, and that's why they fail on very simple things which humans would never. This brings me to the last small bit that I want to mention before we close, which is this big models actually depend a lot on large amount of data. The bigger the number of parameters, the more data you need to train them, right? To solve an equation in three variables, that is three parameters, you need at least three equations. So for a billion parameters, you will need at least billion equations, right? So billion inputs. So that's a bad analogy. You will need much more, several orders of magnitude more, because uh, the the inputs have to be independent, and in this case they are not. Most of language is the same thing repeated again and again and again. On the other hand, the amount of data available in various languages is very skewed. So if English data, the amount of data available for English is represented by this big circle, blue circle, then Chinese is the red one, French you see, and Hindi is so tiny, and Tamil is almost invisible. And we did a study, in a more detailed study of how much data exists in various languages, and we could divide the languages into 6 classes. And class 0, which has around 1.2 billion speakers and around 2000 languages, 88% of the world's languages have absolutely no resources to train any model whatsoever. And it's only class 5, where there are only 7 languages and 2.5 billion speakers, where you can build such models. And very few Indian languages have good amount of resources. So Hindi is there. I think Hindi is there in class 4, Hindi and Bengali. Tamil and Marathi are in class 3. Rest of the Indian languages are in class 2, 1, and most Indian languages are in class 0. So all these benefits are going to only some languages, and that's dangerous, because languages are getting extinct, and this is actually increasing the skew, and more languages might start getting extinct soon. My language has no support on the phone, and I can't use anything, and there is another language which has, so I will move to that language. So that's how people think, and therefore languages might die even more quickly. So the other project we kind of do in our group is Project Ellora, where we try to enable the speakers of low resource languages. How we can do technology for helping the speakers, what kind of things they need, and how we can do it minimal resources. Um, and let me leave you with this thought, that this is a quote from Subbarao Kambhampati. He's a very famous AI scientist, and he was the president of an organization called Triple AI, one of the top organizations of AI scientists. And he said, our systems seem happiest either far away from humans, like the Mars rovers, or in an adversarial stance with humans, like when you are playing a game of chess. But why can't human and AI cooperate and complement each other's skills, right? Why you have to think of AI as either imitating human or beating human? You could actually build much better and useful AI system just by complementing what humans can't do, and what humans do better, like language and all that, let humans do. And that's a very interesting thought of how to optimize, thinking human and AI as a single system, rather than only optimize AI or uh, the machine. Yep. So with that, let me close and with a short announcement that I talked about Linguistics Olympiad and showed you an example problem. So this year's first round is going to be on 26th February. Uh, Registration will open soon. You can log on to our Facebook page, or I mean we post information there, or there's the website link too. Yep. Up for questions. Let me see. So um, there is one question from Arpita. Um, you are asking, do you think AI systems can start correctly understanding grammar and be a potential threat of being mistaken for being human? AI systems. I mean, this is a very good question. It's not about understanding grammar. As I said towards the end of the talk, you probably asked this question before I said, or in the latter half, that AI systems can understand grammar. It can't understand language. Understanding grammar and understanding language are different things, slightly different things. Understanding grammar is about understanding patterns, right? How words are put in a sentence. Now the question is, can is there a potential threat of being mistaken for a machine mistaken for a human being? Absolutely yes. And this is a danger. I mean, I don't know if you know, there was this Google Assistant which was booking an appointment at a salon for a person, and it behaved in a way with even the human disfluences. It said things like which a machine shouldn't say, but it was saying just to pretend as if it was human, and it backfired. Sundar Pichai was showing this, and it backfired. The whole community said, AI shouldn't do this. AI shouldn't pretend to be human. It should make very clear that I am AI. And And there are other potential threats, right? Data, your personal data. So Alexa might be listening to you all the time, and it might hear all things, which even secret things that you don't want to share with Alexa. So what data it is collecting and all should be made transparent. So there are lot of conversation around what machines are doing should be all very transparent and explained properly to humans. Mm, then uh, ingenious crab says, okay, not an octopus but a crab. The new code completion AI based tools seems to be good example of cooperation. Yes, absolutely. There are many examples of cooperation based tools actually. Even if you think of, very simple examples like spell checking is an example of, cooperation. Text prediction is an example. So it gives a prediction, but you at the end choose or not choose. So it's helpful. So most of the AI which is helpful are the ones which are in work in a cooperative mode like this. Okay. So Rudranil Saha has a very long question. Let me read it out. How important do you think developments in the field of neuroscience are for development in the field of NLP? Do you think that understanding the biological systems responsible for learning, perception, and consciousness is key to understanding how to model natural language just into machines, and by extension, solving AI as a whole? Great question, Rudranil. Thanks for asking this. Um, so there are first a quick answer would be the current models of AI do not rely on our findings on neuroscience. There are two reasons for this. First is neuroscience has a long way to go because we really don't understand human brain that well today, so that we can model it. Uh, there are lots of knowledge and people, I mean, lots of things we know in bits and pieces that people try to use, but people have not been super successful. On the other hand, just pumping data and making bigger models have been more successful. But will this be the trend forever? I personally don't think so. So I think going forward, right? I mean, this bigger and better thing will at some point hit what is called the law of diminishing return. So then after that, making things, to increase the performance by delta, you have to make it, much, much bigger, and we can't do that. So eventually things like, logic, rule, and information, like how humans process information in the brain, will become very useful. So I think we are not yet there, but eventually it will be very, very useful. And people are already talking about it. People have been talking about it for a while, but as I said, there are no good examples of this in action. Okay. Um, Veer asks, how do you see the concept of chatbots and advertisements changing with the metaverse and other virtual world? Would an AI which passes the Turing test in the virtual world be more dangerous? Yeah. So this this is also a very interesting question, and it all depends on how the world looks like in the future, right? And the way things are moving, where things are getting more and more virtual. I think you know in a virtual world, it might not only be dangerous, it might be more dangerous because it's also more easy to pass the Turing test in a virtual world than a real world. And then it becomes really a complex thing to sort out. But this is like something very I would say a little more futuristic, and I yeah let's see, time will show this. uh, uh, in how many years do you think deep learning can completely understand language, including normal human terms? Null exception. So you are using a word understand. Now, if I were to define understand in the way humans understand, you know, then the answer is going to be very tricky, because so far there is no signs of these machines understanding anything, primarily because we are not, what, as I said, we are not grounding them, right? So grounding means connecting the meanings to the real world, Right now the meanings are not there. It's like only text or only speech or maybe sometimes image and text. So it's all like some sort of bits and bytes which they are correlating, but there is no real world or a model of real world in which the AI is reasoning. So therefore it's hard to say whether I mean, we shouldn't say that they are understanding anything. Now if your question is whether they will understand like humans do ever and when, I don't know. I'm not, I mean, many people say it's never possible. I won't say that. It might be possible. We might understand human brain better. We might understand understanding better. And therefore, in some time in the future, this might be possible. But it's far, far away. But if you are saying, completely understand, meaning seemingly understand, it's able to process, then we are almost there. Maybe in another 10, 15 years, most of the problems that I'm talking of will have reasonable solutions or at least practical solutions. Mm, do you think AI can be used and directly applied to solve linguistics Olympiad problems? That is, although problems are made to be self sufficient, there is still some linguistics intuition needed. Vlad, thanks for this question. By the way, Vlad is the Linguistics Olympiad organizer for Hong Kong and closely knit to the family. He's also part of EPLO, and I know him very well. Yeah. So, Vlad, so Sojas and I worked on this problem. So, Sojas is another person who is closely related to Indian Linguistics Olympiad. And we tried solving linguistics Olympiad problems using AI. Now, needless to say that, the neural models or machine learning models fail very badly because the amount of data present in a typical linguistics Olympiad problem is far smaller than what these machine learning models assume. Now we tried other classical models like combination of machine learning plus rule and those kind of models to solve, and they can solve, but they do require what we call a domain specific language or domain specific knowledge, which essentially is linguistics intuition which you are mentioning. So yes, to solve linguistics Olympiad there is a non-trivial amount of linguistics intuition that is required, especially if you want to solve them from this much data only. But of course, the same problem, if you had given a lot more data, let's say instead of in the Yongam English problem, instead of 11 data points, if you had given me 11,000, then the machine could have made, solved it even without much of a linguistics intuition. But of course, it will not be 100% correct. Mm, Lame Sap is asking, if we were to let deep learning talk with the internet, with social media, assuming it was intellectual talk, could it be better than it is currently? I'm assuming you are saying, I mean, this is kind of related to the Facebook example, right? You are meaning that what if we made a bot which can talk, and instead of talking to itself, it talked to people through the social media and internet. Would it become better? It would. Remember the data driven thing I told you, right? As you interact more with humans or users, you become better, the AI systems become better. So it would certainly get better, but there are pretty infamous examples too, not only the Facebook one. But I don't know how many of you have heard of a chatbot called Tay, which Microsoft had launched on Twitter, and within 48 hours it had become extremely racist, and it had to be Microsoft had to shut down that project, and a lot of controversies were around it. Now, why a chatbot would become racist, right? Microsoft would not never ever make a racist chatbot. So why? So it was because it was learning by talking to people, and there was a group of people who wanted to make it racist, and they kind of uh, threw a lot of racist comments on it, and eventually it learned from that. So learning from social media has both its pros and cons, and we have to do it really, really carefully. So Tay is a great example to remember in this context. Models like GPT-3 are essentially horizontal scaling, increasing parameters, training on more GPUs. But what we call AGI is vertical scaling, first principles thinking, more data, uh, uh, or better. Okay. What breakthroughs in technology other than NLP do we need to get AGI? So This is a good question, Somesh, and a good observation that models like GPT-3 will probably never crack AGI, and the community understands this. Um, Now, what requires to be crack AGI is what we don't know. So there is, I mean, the my personal thinking, and there are many people who think similarly, is that we need hybrid systems. So there's a very famous book, Thinking Fast, Thinking Slow, by Dan Kahneman, right? Daniel Kahneman. He's a Nobel laureate, and it's a great book where he says that brain has two systems. Right now, I mean, typically it's referred to as system one and system two, and one of the system reacts immediately. When I see let's say a scene, or when I'm reading something, it's not that I'm applying some conscious logic to sort that out. So this kind of things are better done by things like neural network or deep learning, and there that's the real benefit. Whereas the type 2 system is more a meta logic on top of this system. So when you were to solve the vinaigrette challenge, right, the man could not lift the son, or the child, he was too heavy. Now you had to think for a second. It was not immediate. That second that you took to think, right, that was your system 2 kicking in. So system 2 is something which these models can't do. All the logical examples of NLI that I had shown you, A and B are respectively from country 1 and country 2. If you try to solve this kind of problems, or linguistics Olympiad problems, you can't solve them instinctively. So there is a part of language which is instinctive, and there is a part of language which requires reasoning. So the instinctive part is something which GPT-3 can solve probably very well, but the reasoning part is what it can't. And for that, you need to build, symbolic system, as we call it, rule-based symbolic system, where you are reasoning over set of symbols. And um, what other things do you need to solve NLP, other than NLP? See, I mean, there are 2 points when I say NLP is equivalent of AGI. Um, one interpretation of that is you solve NLP and you get, let's say, a machine which has AGI. That's not the meaning. The meaning is, if you can manage to solve NLP in its full blown, avatar, then you have all the components required to solve AGI. You have all the algorithms. Now you will also have to solve vision, because it has to see. You will also have to solve few other things, right? Mobility, this, that. So for this, you have to do separate training, but at least you will know what to do. So that is the point. So if you solve NLP, you will know what to do, what should be done, but doesn't mean that it will be all done. So still people have to build and train those systems. Aryaman asks, in the chess example where the same bot was playing against itself, how long would the bot take to be able to beat anyone? I don't know the details, Aryaman. You can see, but I mean, you can read, but there are, in reality, these bots were not instantiated with only the rules of chess. They were instantiated with some data from experts. It started learning from that, and then you have some initial bot, let's say baseline bots, and then it started playing with each other, right? So it will depend on a lot of things: how good the baseline bots are, and how complex the game is, and all that. So I would imagine it could take something between 1 million to 1 billion games that it plays against itself. But yeah, I'm not sure of the exact number. Yep, I think that's all the questions. And thanks a lot for asking all the very interesting questions and making it interactive.
Thank you so much, sir, for joining. It was great to have you here with us, and I'm sure the participants learned a lot. I know I learned a lot. and we'd love to have you in the future. Thank you everyone for joining, and have a nice day.